You know, I feel like we like to think of modern software architecture like physical engineering.
Right, like pouring concrete or
Yeah.
something.
Yeah, exactly. Like you build a skyscraper, you pour this massive concrete foundation, you bolt the steel beams together, and you trust that the floor isn't going to suddenly vanish beneath your feet.
You'd certainly hope not.
Right. But looking through this stack of threat intelligence reports we have from April 2026, it becomes really clear that enterprise architecture is not a skyscraper at all. It is, frankly, a massive teetering Jenga tower.
Oh, for sure. It really is.
And those foundational blocks at the very bottom of that tower, those are just shared infrastructure and open source libraries.
Yeah. And right now, we're basically watching malicious actors aggressively pull out those foundational blocks. And meanwhile, the rest of the industry is busy trying to build these shiny new AI penthouses on the top floor.
Which is a terrifying visual, honestly.
It is. It's a profoundly fragile ecosystem.
Yeah.
And the sheer speed at which it's being compromised right now, it's shifting the entire paradigm of enterprise risk for you, the listener, whether you realize it or not.
So true. Okay, let's unpack this because we need to start right at the foundation of that Jenga tower. There was just a critical vulnerability disclosed that impacts GitHub.com and GitHub Enterprise server.
Yeah, the big one.
Right. And for any development team listening, GitHub is the concrete. It is the bedrock where the world's proprietary code lives. And researchers at Wiz uncovered a flaw that turns like the most mundane action imaginable into a catastrophic breach.
It really is wild when you look at the details.
We are talking about a developer simply typing a git push command to upload their daily code. Just a standard push.
Yeah, and that's a reflex, right? You do it 20 times a day without even thinking about it.
Exactly.
But this specific vulnerability, which had a CDSS score of 8.7, by the way, it allowed an authenticated user to gain full remote code execution on the server just by pushing code.
Wow.
And the mechanics of how that actually happened, well, they expose a massive systemic blind spot in how modern microservices actually communicate with one another.
Right, so let's unpack that mechanism because from what I read, it comes down to this tiny piece of internal metadata, something called an XStat header.
Yes, the XStat header. So when you push code, your user inputs are taken and basically stuffed into this header. It's essentially a tracking note.
Like a sticky note passed between servers.
Exactly. GitHub's internal services pass it around to each other to coordinate the whole operation. But the delimiter they use to separate the different commands within that header, it was just a semicolon.
Wait, really? Just a semicolon?
Just a standard semicolon. A character that literally anyone can type into their user input.
Oh, man.
So by simply typing a semicolon, an attacker could basically break out of the intended data field, and then they could start injecting their own metadata. They were suddenly speaking directly to the internal services in their own internal language.
Okay, I want to make sure we visualize the concept of this internal bypass correctly, especially for you listening who might not be a developer. It's like sneaking a master key into a high-security hotel by hiding it in your luggage tag.
I like that analogy.
Yeah, and suddenly you can open every single room. Like, the bouncer at the front door checks you thoroughly, but once you're inside, if you start passing notes to the bartender using the staff's internal shorthand, in this case, semicolons, the bartender just immediately assumes you are authorized management.
What's fascinating here is the architectural flaw behind that. The attacker wasn't breaking through the front door of the server at all. They were tricking the internal systems into executing arbitrary commands just by impersonating authorized internal traffic.
So they were already inside the club, basically.
Exactly. And by chaining a few specific injections together, things like altering the railsem variables to bypass sandbox protections, and then redirecting the custom hook stirrer and repop receive hooks, they effectively wrote instructions that the server executed as if it were the administrator.
So they end up with full unsandboxed control over the GitHub Enterprise server instance. They can read the file system, alter code, pull internal configurations, the works.
Yeah, absolute works.
But wait, I have to challenge the core premise of this architecture. Why do massive multi-tenant platforms like GitHub still implicitly trust internal data? Like, why does this matter to the listener who just browses the internet and doesn't code? We talk about zero trust all the time. Shouldn't every single microservice be treating incoming data as hostile?
Well, in a perfect world, absolutely. That is the literal definition of true zero trust architecture.
Right.
But migrating legacy, highly complex, globally distributed platforms to a zero trust model internally, it is incredibly difficult and expensive. Historically, the prevailing engineering logic was just to build an impenetrable perimeter,
Yeah.
Make the inside a safe, trusted zone so things can process faster.
Make the outer shell hard, but the inside is just soft and squishy.
Exactly. And this vulnerability proves just how dangerous that legacy thinking has become. Because obtaining code execution on GitHub.com, that allowed for massive cross-tenant exposure.
Which means what exactly for the average company?
It means an attacker could theoretically read millions of repositories across that shared storage node. If your bank or, say, your healthcare provider stores their code there, it's entirely exposed. The attack completely disregards user or organizational boundaries.
Man, that is an enterprise nightmare. Now, to be clear on the facts, GitHub patched this on their main site within 2 hours of it being reported by Wiz on March 4th.
Which is an incredibly fast turnaround.
Yeah, and there's no evidence it was exploited in the wild. But it stands as a glaring reminder that a single unchecked semicolon can threaten the foundation of the modern web.
It highlights that the foundation is just far more porous than we really want to admit.
Yeah. But while the good guys caught that foundational flaw before it could be weaponized, the reality at the very top of our Jenga tower is, well, it's much grimmer. Because that shiny new AI layer the industry is building right now, threat actors are attacking it with terrifying velocity.
The speed of exploitation in the AI infrastructure space right now is totally redefining the concept of response window. It's unprecedented.
Let's look at the second source we have, the Berry AI LiteLLM vulnerability. For context, LiteLLM is a highly popular open-source AI gateway. Basically, it acts as a proxy or like a traffic cop.
A very busy traffic cop.
Right. If an enterprise is building an AI application and they want the flexibility to route prompts to OpenAI, Anthropic, or AWS Bedrock interchangeably, they put LiteLLM in the middle to manage the connections. And it just got hit with a critical SQL injection flaw.
A CVSS 9.3 to be exact. Extremely high severity.
Yeah.
An unauthenticated attacker could send a specially crafted authorization header to any language model API route. Something as simple as a standard chat completion request could exploit a vulnerable database query through the proxy's error handling path.
And the mechanism here is surprisingly basic for such a modern tool, right? During the proxy's API key check, the database query was just taking the key value supplied by the caller and mixing it directly into the query text itself.
Yep. Rather than passing it safely as a separate sanitized parameter, it is a textbook SQL injection.
Wow.
The exact same vulnerability we've been warning developers about for 20 years, but now it's sitting right in front of extremely modern, high-value AI infrastructure.
Okay, but hold on, let me push back a bit. If LiteLLM is just an open source tool acting as a middleman, shouldn't the actual foundational model providers like OpenAI or Anthropic be the ones securing these API keys? Like, why is a database leak such a catastrophe for this lightweight middleman?
Well, because the enterprise market demands flexibility, and the major providers aren't really incentivized to offer it. Companies want to be model agnostic.
Right, they want to mix and match.
Exactly. They want to switch between OpenAI and Anthropic on the fly based on cost or performance. Since the major tech giants don't offer a universal cross-platform traffic cop, the open source community built one.
Makes sense.
But the architectural flaw is that to do its job, that proxy must hold the actual unencrypted credentials for every single platform it connects to.
Oh man, which makes that proxy database a massive, centralized honeypot.
An absolutely irresistible one. And the speed of the attack reflects exactly how valuable that database is. Within just 36 hours of the advisory for this flaw being published, threat actors from two specific IP addresses, 65.101.27.132 and 65.11.25.67, were actively exploiting it in the wild.
That timeline is what really changes the game for me, 36 hours. But here's where it gets really interesting. When you look at the logs, the behavior of the attackers wasn't just, running automated, noisy scripts to smash and grab everything in the database.
No, it was surgical. Highly specific and deliberate.
Yeah. They went straight for specific tables. They targeted ones named LiteLLM credentials.credential values and LiteLLM config. They completely ignored standard user tables.
They knew exactly where the gold was buried. If we connect this to the bigger picture, a single row in that credentials table could hold an OpenAI organization key with a 5-figure monthly spend cap.
Right. Or an Anthropic console key with full workspace administrator rights.
Exactly. And the blast radius of this extraction isn't just an application crashing or a temporary service outage. If an attacker extracts those keys, they can spin up tens of thousands of dollars in compute charges on your infrastructure in a matter of hours.
Just burning through your budget.
Or worse, they can access the proprietary, sensitive corporate data you are feeding into those models. It is closer to a total cloud account compromise than a simple software bug.
What this really illustrates is the total collapse of the patching window. Historically, an enterprise security team assumed they had time. Like, attackers would usually wait for security researchers to publish a proof of concept exploit before they launched a widespread attack.
Yeah, that era is officially over.
It really is.
The operator behavior in this LiteLLM attack proves that the public advisory and the open source schema alone were enough. The attackers read the alert, looked at the public code repository, wrote their own custom exploit, and fired it off in under 36 hours.
So if your enterprise IT team logs off for the weekend when a vulnerability drops on a Friday afternoon,
Your AI infrastructure is already fully compromised by Sunday morning. Gaining access is happening at light speed right now.
but gaining access is only the first phase of the business model for these cyber criminals, right? They move at breakneck speed to steal the data. But what happens when they decide to monetize that access by locking up a company's data?
While sometimes they fail spectacularly.
Yeah, let's pivot to the final intelligence report in this stack, because this is where the threat landscape shifts from terrifying to, frankly, genuinely absurd.
It really is. We're talking about VECT 2.0.
Right, VECT 2.0. This operates as a ransomware as a service, or RAS model. They run affiliate programs, charging an entry fee of $250 in Monero cryptocurrency. Their whole pitch on the dark web is super polished. They market themselves as exfiltration, encryption, extortion.
Very corporate. They present themselves as this highly industrialized professional operation. They even establish formal partnerships with major hacking groups, like Team PCP.
Wait, isn't that the same group?
Yes, the exact same threat group doing supply chain attacks in the LiteLLM story we just discussed.
That's wild. So you have a group that looks incredibly sophisticated on paper, but then Checkpoint Research gets their hands on the actual malware, decompiles the C++ code, and finds a massive twist. VECT 2.0 is actually not ransomware at all.
No, it is a data wiper.
A wipe.
And it is not a data wiper by design or ideology.
Yeah.
It is a wiper entirely due to sheer incompetence in how they implemented their core encryption logic.
Okay, we need to break down the mechanism of this flaw clearly, because the logic error is just bizarre. Let's look at how the malware handles large files. For any file over 131 kilobytes, which is practically every document or database an enterprise actually cares about, the malware chunks the file into pieces to encrypt it faster.
Right. It uses the CHA-20 IETF encryption standard. And for each large file, it generates 4 independent, randomly generated digital locks called nonces to secure those 4 distinct chunks.
But here's the fatal coding error. The malware only appends the key for the final lock to the encrypted file. It silently discards the unique keys for the first 3 chunks.
It literally generates the mathematical keys required to unlock the data, uses them once during the encryption process, and then immediately throws them away.
Unbelievable.
It doesn't save them to the local disk, it doesn't write them to the Windows registry, and it doesn't even transmit them back to the attacker's own control panel.
It's like a kidnapper putting a ransom note on a safe, locking it, but accidentally throwing the only key into the ocean before they even leave the room.
That is exactly what it is.
Right.
Because that specific encryption standard strictly requires both the master key and those specific discarded nonces to reverse the mathematical process.
So the first 75% of every single large file is destroyed permanently. Nobody can decrypt it, not the victim and physically not the hacker. So what does this all mean? How is a victim supposed to respond to this?
Well, this raises an important question about who exactly is running this operation, because it completely invalidates their own business model. If a victim pays the extortion fee, the attackers physically cannot provide a working decryption tool. The information required simply cease to exist.
Which brings up a massive contradiction, because on the surface, the VECT 2.0 Windows variant has this massive anti-analysis suite. It has 44 different checks to evade enterprise security tools. It writes itself into the registry to force a safe mode boot. Who builds a sophisticated evasion tool but completely botches the basic encryption loop?
Checkpoint's assessment is that the actual developers might be complete novices. And there's a glaring anomaly in the Linux and ESXi versions of the malware that supports this. Those versions enforce geofencing. They check the machine's location to avoid encrypting files in certain countries.
Which used to be standard practice for Russian-speaking ransomware groups, right? To avoid triggering domestic crackdowns.
Key phrase. Used to be. VEC 2.0 includes Ukraine in its exclusion list.
Oh, wow.
Yeah. Almost all major ransomware as a service programs purposefully removed Ukraine from those lists years ago, right after the invasion in early 2022. It is a highly outdated practice.
So either this group bought a really old, repurposed code base from a defunct cartel.
Or, and this is the theory gaining a lot of traction, these novice developers use an AI large language model to help them write their malware. And that AI was trained on outdated geopolitical data and flawed, incomplete encryption implementations.
That is incredible. I mean, it's genuinely amusing. They might be utilizing AI to rapidly code their malware only to inadvertently build a tool that physically prevents them from ever getting paid.
It's the Dunning-Kruger effect weaponized on a global scale.
Absolutely. But for an enterprise IT leader listening to this, the operational takeaway is brutal. If you are hit by a VECT incident, paying the ransom is completely useless.
It is worse than useless. It's a waste of critical recovery time. The data is fundamentally gone. Your only viable recovery strategy is relying on offline backups and rapid network containment.
Okay, let's pull all these threads together. This stack of intelligence reports paints a very vivid and slightly chaotic picture of our digital Jenga tower. We started down at the foundation, where a single misplaced semicolon could expose millions of proprietary code repositories across GitHub's shared backend.
Then we moved up to the application layer, watching threat actors weaponize vulnerabilities in open-source AI gateways in under 36 hours.
Bypassing the need for public exploits entirely. And finally, we looked at the monetization phase, where heavily marketed ransomware operations are permanently destroying the very data they were trying to hold hostage, all because of copy-paste AI-generated coding errors.
Exactly.
To you, the listener, the folks actually tasked with designing and defending these networks, the major takeaway is that our digital infrastructure is a fragile ecosystem. Relying on traditional assumptions is a dangerous illusion.
The assumption that internal network traffic is inherently safe. The assumption that you have time to patch an open-source proxy tool. Or even the assumption that a cybercriminal demanding millions of dollars actually understands how to decrypt your files.
They're all false comforts. And looking at the sheer speed and chaos across these three reports, it leaves us with a pretty wild final thought about where this is all heading.
Yeah. I mean, if cybercriminals are now potentially relying on AI to write their malware and making catastrophic business-ruining mistakes like throwing away their own decryption keys, what happens when AI systems on the defensive side start finding and patching vulnerabilities faster than the attackers can exploit them?
Wow.
Are we moving toward a fully automated cyber war where human incompetence is the only real threat left on the battlefield?
If the bots are fighting the bots at light speed, the only vulnerability left is the human typing a semicolon in the wrong place. Or a hacker fundamentally misunderstanding how their own encryption library works. It is a fascinating, terrifying frontier. Thank you for joining us on this deep dive. Keep questioning the structural integrity of the technology you rely on every day. Verify your offline backups are actually isolated. And remember, just because the floor feels solid under your feet today doesn't mean the foundational blocks aren't shifting. We'll catch you on the next one.